Alright, here we are with part 2. In part 1, we looked at the field HbyA in quite a bit of detail and actually tried to understand what it physically means and how we calculate it. In part 2, we're now going to be looking at what HbyA is actually used for, how we can use it to derive the pressure equation, and what additional calculations we actually need to do as part of the overall pressure-velocity coupling algorithm. So let's get back and get into the video and have a look in more detail about HbyA. Now, before we start looking at HbyA and the pressure equation again, we need to have a think about differential equations. If we think of a differential equation like the incompressible continuity equation, these differential equations in differential form are continuous, which means that they're satisfied at every single location in the domain. If you think of the domain as divided up into a series of infinitesimal points, the differential equation is satisfied at every single point in the domain. And that's going to be very important for us going forward. So similarly, if we think of the incompressible steady Navier-Stokes equations, these equations are satisfied at every single infinitesimal point in the domain. And physically what that means is that at every point in the domain, the velocity vector and the pressure field satisfy conservation of momentum. Or more specifically, the Navier-Stokes equations represent a local balance of forces per unit volume at a given point in the domain. And another way you can think of this is if you were to substitute in a velocity vector and a value of the pressure field, then at that location, the momentum from that velocity field would balance the pressure gradient and all of the terms in the equation, and momentum would be conserved. And when we have our converged solution, the Navier-Stokes equations are satisfied at every single individual point in the domain. And that's going to be very important for us going forward. Now, when we come to solve the equations in fluid dynamics using the finite volume method, what we do is integrate these differential equations over the volume of a cell. So physically, when we create our computational mesh and we divide the domain into a series of cells or control volumes, what the finite volume method does implicitly is integrate the equations over the volume of that cell. That's what the method is physically doing. And so if we think about the two different forms of our differential equation, when we have the equation written in its differential form, like the Navier-Stokes equations, for example, the Navier-Stokes equations represent a local balance of forces per unit volume at every single point in the domain, whereas when we integrate that equation over the volume of a cell, we now have a balance of total forces acting on the entire cell. And a way you can think of that is if you were to consider a point in that domain which represents the balance of forces per unit volume, you multiply it by the infinitesimal volume, and then you repeat that process over all of the infinitesimal volumes in the cell and add them up. Of course, the total, or the integral, would be equal to 0. The total force acting on all of the volumes within that cell is equal to 0. And this distinction is going to be very important for us when we're looking at the pressure equation and HbyA. The equation, the Navier-Stokes equations written in differential form, represent a local balance of forces per unit volume, whereas the integrated form represent the total forces acting on the volume of the cell. And the reason that's going to be important is when we think about the form of the matrix equations that we were considering in the previous lecture. So when we have the integrated Navier-Stokes equations like this and we apply the finite volume method, that ends up resulting in one of the rows of the matrix equation. So for example, if we integrate the Navier-Stokes equations over cell 1, then we apply the finite volume method, the divergence theorem, and rearrange the various terms as we've done in previous videos, that then results in the first row of the A matrix multiplied by the column vector, and that gives us the unknown source term on the right hand side. So it's this process that allows us to convert our differential equation into matrix form that we can then solve using a computer. And the implication of this understanding is that each row in the matrix equation represents the total balance of forces acting on an individual cell in the mesh. So row 1, for example, represents the total balance of forces acting on cell 1. Row 2, multiplied by the column vector u, of course, will represent the total balance of forces acting on cell 2, and so on. And this important distinction between what the row in the matrix equation represents and the original differential equation is going to be important for us later when we derive the pressure equation. So in part 1 of this talk, you may remember that we just considered an example 2D mesh with 6 cells, labelled from 1, 2, 3, 4, 5 and 6, and we're in the XY plane. And what we would like to do for this example mesh is derive the pressure equation for cell 1. And you may recall that what we did in the previous talk is we extracted the first row from the U and V matrix equations and wrote them out in algebraic form, and we resulted in two equations, 1 and 2. We've got A11, U1, that's the diagonal element is A11 multiplied by U1 plus A12, U2 plus A14, U4 is equal to the right-hand side. And you may remember we separated out all of the source terms and we separated out the pressure gradient force, so the cell volume V1 multiplied by the pressure gradient, we separated those two contributions to the B vector out. And we did this process for the U momentum equation and the V momentum equation. And from the brief introduction that we went through today, we now know, of course, that these two equations represent the total balance of forces acting on cell 1. Of course, equation 1 represents the X component of that force, and equation 2 represents the Y component of the total force acting on cell 1. And what we then did was we divided all of the terms in equation 1 and equation 2 by the cell volume. And as well as dividing by the cell volume, for convenience, we also introduced a lowercase notation for those A matrix coefficients, and that allowed us to write equation 1 and 2 in the form which you can see here on the slide, equation 3 and 4. You notice the equations are very similar, but we've now got the lowercase a for the matrix coefficients, lowercase b1, and the volume, the cell volume is missing now from the pressure gradient term, which you can see there. But the key point and the key takeaway from this slide is that the equations now have units of force per unit volume. So when we extracted the equations directly from the matrix equation, because they represent the total balance of forces acting on the cell, all of the terms in the equation have units of force, but now because we've divided by the cell volume, these equations now represent the force per unit volume. So you can probably see what we've done here with this rearranging of the terms is we've moved from the total force acting on the cell to that local force per unit volume at a location within the cell. And this subtle difference is very important for when we derive the pressure equation. Now, as well as dividing by the cell volume, the other thing that we do for convenience is divide all terms in the equation by A11, where A11 is the diagonal A matrix coefficient divided by the cell volume. And when we do that, we arrive at equation 5 and 6. These equations still represent the balance of forces per unit volume at an infinitesimal location within the cell, but of course now all the terms have units of velocity. We went through that before. And rearranging the equations in this form allows us to introduce the terms h1x and h1y, and you'll remember from the previous talk that HbyA is used to identify all of the terms on the right hand side and collect them together that doesn't include the pressure gradient. So all of these off diagonal matrix terms and the source term, we collect all of those together into this h1x and h1y terms there. And we went through in the previous talk in a bit more detail what this term physically represents. But we're now in equation 7. We've still conceptually made the same series of steps. We've just taken that equation out of the matrix equation, divided by the cell volume, and then rearranged in terms of the unknown velocity component there. But this still represents conservation of momentum, or the balance of forces per unit volume at a location within the cell. And it's useful, I think, to think in terms of a diagram here, that when we originally extracted that equation from the matrix, we've got the total balance of forces acting on the cell. But now that we've divided by the cell volume, we're now thinking about the local balance of forces at an infinitesimal point within the cell. That's the important thing. And the other thing we can do, which we didn't do in the previous talk, is because we've got an equation for the x velocity component u and an equation for the y velocity component v, we can of course combine these two equations together in vector form, and this now represents the local velocity vector at a given point within the cell that balances the local forces per unit volume. And I choose to use bold notation here for vectors rather than using an arrow over the top. You can see we've just combined the velocity components together. The components of HbyA are combined together, because remember this is a vector quantity, and the components of the pressure gradient are combined together into the pressure gradient vector, which you can see there. And you may have come across equation 9 before. You may see this in some of the sources or some of the references, but it's really helpful to think about what the terms in this equation actually mean. And I usually think of this in terms of a vector addition or a velocity triangle. You may hear people refer to it as this. And the way I think of it is, if you think of a local point within your cell volume, we have a velocity vector there, u1, which has a magnitude and a direction. And of course that velocity vector is equal to the sum of the other vectors, h1 by a and minus 1 over a1 times the gradient, the pressure gradient. And this really helps to understand and summarize what the HbyA term actually means. It still represents a velocity vector, and you can think of it as the velocity vector that would exist at that location in the cell if the pressure gradient wasn't there at all. So that's a useful way of thinking about what this equation actually means. It's just a vector triangle, which is another way of expressing the velocity vector. And it turns out that this representation of the velocity vector is really useful for a simple, easy derivation of the pressure equation. And in order to derive the pressure equation, we're going to need the continuity equation as well. So regardless of which methodology you use to derive your pressure equation for CFD, whether you use the method used by OpenFOAM or another code, the idea is always the same. The idea is to combine the continuity equation with the momentum equation, and that results in the pressure equation. And all of the algebraic manipulation that we've done so far in this talk and in part 1 is to make this combination and derivation a lot simpler. We're going to see that in the next few slides. So equation 11 here is the incompressible continuity equation for cell 1. The divergence of the velocity vector within cell 1 is equal to 0. And if we think right back to the start of the talk, you'll remember that this equation is written in differential form. It's not integrated over the volume of the cell, which means that for a converged solution, this differential equation will be satisfied at every infinitesimal point within the cell and also every infinitesimal point within the entire domain. And what that means now is that because we've got our continuity equation in differential form, it's satisfied at every single infinitesimal location within the cell, and we've also got our momentum equation, which is also written in terms of an infinitesimal location within the cell. It's not integrated over the volume of the cell. That means that we can combine these two equations together because they're both going to be satisfied at every single infinitesimal location within the cell. And it turns out combining them together is very simple. You can see we've got the divergence of u1 is equal to 0, and we have an equation for u1. So we can just substitute those terms into the divergence operator. So we go from equation 12 to equation 13. We've just substituted in the momentum equation there for the velocity vector. And then what we do is just separate these two terms and bring them to the other side and rearrange, and we arrive at equation 14, which is the differential form of the pressure equation that's used in OpenFOAM. And hopefully from this slide you can see that actually we did a lot of upfront work and thinking about what the terms in our momentum equation and our continuity equation actually mean. And by doing this, even though we put in a lot of work, the result was that the derivation of our pressure equation was actually really simple. It was only 3 equations to arrive at the pressure equation. So there are definitely some conceptual benefits in deriving the pressure equation in this way. But before I move on in the talk, let's have a think and have a look at the pressure equation and what form it's taking and what terms are actually present, because this is really going to help our understanding. We can see on the left-hand side, we have the divergence of 1 divided by the diagonal matrix coefficient from the momentum equation per unit volume. So this is the first way that the momentum equation actually forms part of the pressure equation. This is something quite unusual. A11 isn't a geometric feature or a material property of the flow. There's no density in here or areas or conductivities or anything. This is a coefficient which is extracted directly from the matrix equation. So this is something which you may not have seen before. And that's multiplied by the pressure gradient in there. And as is standard, the left-hand side of our equation represents the unknowns that we want to calculate. If we solve this equation, the solution will be the pressure field. The pressure field that satisfies this equation would be the solution of our pressure equation. And the other thing that this equation tells us is that because the left-hand side has got the coefficient of the matrix equation in there, A11, every time a new momentum matrix equation is solved, the pressure equation that we solve is different. This is a really important conceptual idea, is that we're not solving the same equation each iteration. Every time we go round the loop of our simple or pimple or piezo algorithm, the actual pressure equation that we solve is different every time, and it's implicitly linked with the momentum equation that we've just solved. So that's also something new which you may not have thought about before. The actual equation that we're solving is different and changes each iteration. So we've got the left-hand side of our differential equation there, but what about the right-hand side? The right-hand side simply contains the divergence of the field HbyA. And this is exactly why we've gone to all of this effort trying to understand what HbyA is and trying to calculate it. The reason that we need to know these things is because HbyA forms the source term of the pressure equation. So conceptually, you can think of the algorithm as you would solve the U and V momentum equations. You can then take that solution to assemble the field HbyA and extract the diagonal matrix coefficient, and then these two terms become inputs into the pressure equation. And every iteration, we're solving a new pressure equation each time we come around the loop. But of course, we aren't done here yet. We're not finished because the equation's written in differential form. And you'll also remember back from the start of the talk that when we assemble and write the equations in matrix form, they need to be integrated over the volume of a cell. Because currently this equation represents a differential equation that's satisfied at every infinitesimal point within cell 1. But we need to integrate this equation over the volume of cell 1 so that we can get a pressure field solution at the centroid of that cell. So that's what I'm going to be doing for the remainder of this talk. And the other small note that I want to make for this pressure equation as well, some of you may notice just the general mathematical form of this pressure equation. On the left-hand side, we have the Laplacian, and on the right-hand side, we just have a source term, an explicit source term. There's no time derivative here. We don't have an advection term either. We only have a Laplacian term, which mathematically is similar to the diffusion term that you have in the momentum equation. And for this reason, sometimes people refer to the pressure equation as a Poisson equation. It has the same mathematical form as a characteristic Poisson equation. You've got a Laplacian on the left-hand side, and you've just got a source term on the right-hand side. And in general, this is only true for the incompressible flows. For compressible flows, you may have additional terms in your pressure equation as well. But for now, that's the pressure equation in differential form. Let's think about it in integral form. So before I jump into that, let's just quickly summarize where we are and what we've learned so far in this lecture. Well, within a given loop of the simple algorithm, or piezo or pimple, or other algorithms that use a segregated solver, we've solved the u momentum equation, we've solved the v momentum equation, and once we've done that, we calculate the vector field HbyA, and then the vector field HbyA becomes the source term, the right-hand side of the pressure equation, and the matrix coefficients in the pressure equation will be taken from the diagonal entries of the momentum equations. So that's how the pressure equation is formed. We solve the pressure equation, make some assessment of whether we've converged. If we haven't, we go back and we repeat the process again, solving u and v, calculating HbyA, calculating a new source term, solving the pressure equation, and so on until we have convergence. And this is exactly why HbyA is calculated after the u and v momentum equations are solved. It's an explicit calculation because we need it for the source term. What is that source term? Of course, what we need to do is the equation is currently in differential form. We need to integrate it over the volume of the cell, and the way we can do that is just by integrating both sides of the equation over the volume of the cell. And physically, of course, what that means is that we're taking the differential equation and multiplying it by an infinitesimal volume at some location in the cell, and then we move to the next infinitesimal location, evaluate this, multiply by the volume, and so on, and sum all the contributions together. That's what we're physically doing when we're integrating over the volume of the cell. So how do we do this? Well, if we look at this integral looks fairly complicated, but what we notice is that on both the left and the right hand sides we have the integral of the divergence of a vector field on both the left and the right hand sides, and so we can simplify this by using the Divergence Theorem, which is also known as Gauss's theorem. And the way I'd like to explain that to you is just by going through a general application of the Divergence Theorem, what it means, and then we're going to apply it to the equation that we've just seen there. So what I want you to do is think about a general vector field C. And this vector field C could represent anything. It could represent velocity, pressure gradient, it could represent any vector quantity. And I want you to think about a volume or a cell within a mesh. It could take any shape. On this particular slide, I've got a pyramid-shaped cell, and we're going to be integrating the divergence of this vector field C over the volume of our cell. And the only real restriction we have on this is that the cell is an enclosed volume, that there aren't any holes or leaks within it. And what does the divergence of the vector field C physically represent? Well, as a vector field, we have a magnitude and a direction, and if we take an infinitesimal point, the divergence physically represents the net outflow of that vector C from a given location. So I show it as a series of arrows emanating from a given point. If the divergence was greater than 0, more of the arrows would be pointing outwards than they are pointing inwards. If the divergence is equal to 0, the number of arrows pointing outwards would balance the number of arrows pointing inwards, which of course means you have a flow of a vector rather than a net inflow or a net outflow. So at some locations within your cell, maybe you do have a net outflow. You have a creation of the vector field C at some location within your cell. But if you were to integrate all of those across the cell, then you would be creating some amount of the quantity C within the cell. And of course the cell is rigid, it can't move or expand, and what that means is that the creation of that quantity C must be balanced by the flux of that quantity C across the surface. If you're creating C, it has to make its way out of the domain somehow. And so what the divergence theorem says physically, without going through the derivation mathematically, is that the volume integral, or the total source of C within the volume, must balance the flux of C across the surface. And think of this as, if you're creating C inside the volume, it has to leak out somewhere, and the amount that leaks out is equal to the amount that you've generated. That's how I physically think about this. But mathematically, what this allows us to do is to convert our volume integral into an integral over the surface of the cell, which ends up being a lot easier for us to use to generate our matrix equations. So that's our general result, equation 16. It doesn't matter what C is as long as it's a vector or a tensor field. And the next thing we can do is notice that the cells that we have in CFD generally have a finite number of faces. We may have a hexahedral cell, we may have a polyhedra, we may have a pyramid, but generally they have a finite number of faces. And so what that means is that we can replace the general surface integral over the entire surface with the surface integral over each of the faces in turn. And the reason we need to do this, of course, is that the divergence theorem would also apply if we had a smooth, curved shaped cell instead, it would still apply. But for us in CFD, our faces are generally flat and we have a finite number of them. So we replace the surface integral with the sum of the surface integrals over each of the faces. And then the next thing we do to simplify the surface integral is we need to think about the variation of the vector field across the face. And in general in CFD, we know that at best, the vector field will vary linearly across the face. The vector field will also vary linearly between the centroid of the cell and centroids of the other cells, but in general in CFD, the vector field will vary at best linearly across the face of the cell. So if you think of this solid red line here, the solid red line represents the variation of the vector across a face of the cell. And the variation is linear, and we want the integral across the face. So the integral is the area under this solid red line here. But what we notice is that actually, because the variation is linear about the center, if we were to take the value at the face center and multiply it by the area, you can see visually that you'd get the same answer for the integral. The area under this dashed line is equal to the area under this solid line. And actually, it doesn't matter regardless of what the gradient is. If you look at the second image, if you change that gradient, increase it or decrease it, as long as it's pinned at the center and you have the value at the face center, the area under the curve will always be equal to the value at the face center multiplied by the face area. This is a really key and useful result, and formally it's known as the midpoint rule or the midpoint theorem, but I like to think of it visually this way. And what it allows us to do is to bring this result for the divergence theorem together, and we can say that the integral of the divergence of our vector field C over the volume will of course first be equal to the sum of the surface integrals over all of the faces, but we now know that each of those integrals across the face is just equal to the value at the face center, which you can see there in the diagram, multiplied by the face area. So this is a really key simplification that we can use in our pressure equation. Everywhere we see the integral over the volume of the divergence of a vector field C, we can just replace that with a summation over the faces of the cell of the unit normal vector dot producted with our vector field at the face center multiplied by the face area. And why is the unit normal vector here? Why is the unit normal vector here? Well, remember, of course, we have a vector quantity, and vector quantities have a magnitude and a direction. So at that face center, our vector could be pointing in any direction. But what we want for the divergence theorem is we want the component of the vector field that's pointing out of the cell normal to the face. So that's why we take the dot product with the unit normal vector here. That's giving us the component of the vector that's normal to the face that transports C across the face. And another way you can think of this is that if the vector C was parallel with the face, then that vector wouldn't be transporting any of the quantity across the face. So its flux across the surface would be equal to 0. And this is why we need the dot product with the unit normal vector. So we have this result. Let's apply it to the pressure equation and simplify it. This is the differential form of our pressure equation. And of course, on the left-hand side, divergence, we have the integral over the volume of the divergence of a vector field, C. So if we identify this quantity as C, and that's going to be equal to the integral over the volume of the divergence of another vector field. And so we can apply the divergence theorem twice, first to the left-hand side and then to the right-hand side, and this allows us to rewrite the pressure equation in this form. And now you can see that this is starting to get a little bit complicated. Now we're converting the differential form of our pressure equation into a form that we can write into a matrix equation. It's starting to get complicated. We're getting lots of summations and values evaluated at the face center, and we're getting face areas. But what I want to do in this talk is I only want to focus on the right-hand side of the pressure equation, because this is going to help you when you're reading through OpenFOAM source code. The left-hand side is slightly more complicated because we have to do things like Rhe and Chow interpolation to prevent checkerboard oscillations, and I don't really want to go into that in this talk. I just want to focus on the right-hand side. And you'll remember just from earlier in the talk that the right-hand side represents the source term in the pressure equation, and the source term arises from our HbyA field. But what does this source term actually mean now that it's written in this form, and what does it represent? Because that'll be really helpful for our understanding. Well, if we just look at our source term in a bit more detail and think about one of the faces of cell 1. I've got a diagram here, and on the left hand side I've got cell 1, so just for our example mesh, it's a square cell, and cell 1 across this face is connected to cell 2. And once we've solved the momentum equations, the first thing we do is that we calculate HbyA, the vector, at the centroid of cell 1. And we calculate that from the by taking the weighted average. You'll remember from part 1, we take the weighted average of the velocity vectors at the centroids of all of the cells that surround it, and then add the source term, and that gives us HbyA at the centroid of cell 1. We can also repeat the process and get HbyA at the centroid of cell 2. But if you look very closely at the source term, what you'll see is that we need HbyA at the face center, and that's this red vector here. And remember from the divergence theorem, the reason that we need it at the face center because we're calculating the flux of the vector field C, which is now HbyA, across the surface. So we need it at the face center. And the way we can do that is just by simple interpolation. So if the face center here was equidistant between cell 1 and cell 2, then H1/A at the face center here would just be the average of these two terms. We would take half and half, and that would be very simple interpolation, but we could use more advanced interpolation if we wanted. So we start by calculating HbyA at the face center. And then, of course, remember that HbyA is a vector, and you can see this here. Remember, HbyA can be thought of as similar to the velocity vector. It's pointing at some angle to the face. It's not normal to the face. So the next thing we do, once we have HbyA at the face center, is we take the dot product with the unit normal vector, which I've shown here in blue, and that gives the component of the vector HbyA, which is normal to the face. And it's this component which transports quantity across the face. And throughout all of this, I always think it's really helpful to think of HbyA as a velocity vector. You can think of it as a pseudo-velocity vector or a partial velocity vector that's almost equal to the real velocity vector, but there's some difference. And so in the same way that we'd calculate the component of the velocity vector normal to the face, we're calculating the component of HbyA normal to the face. And when we do that, we've calculated the dot product of the unit normal vector with HbyA normal to the face. We've now got the component normal to the face. If we then multiply by the face area, that's giving us the total flux of HbyA across the surface. You can see that there with the grey arrows that I've included there on the image. So what does this flux of HbyA actually mean? Well, I like to think of this again in terms of the velocity vector. Imagine that imagine if we did have the velocity vector. This was the real velocity field here. The velocity has units of meter per second. It represents a distance moved every second. And when we take the component of that velocity vector normal to the face, we've calculated a distance that the fluid will have moved in 1 second normal to the face. And if we multiply by the face area, you can see that we're enclosing a volume here. This is a volume of fluid in meter cubed per second that's being transported across the face. So a volume of fluid that physically moves across that face every second. That would be the volume flux, or the volumetric flux from the velocity field. And for shorthand, this is often referred to as the flux of HbyA. You can think of it as the physical volume of fluid that's being moved across the face by HbyA, if HbyA were the real velocity field. And you can see this just in the notation that's used by OpenFOAM as well. OpenFOAM refers to the volumetric flux as phi, and phi being the dot product of the unit normal vector and the velocity vector multiplied by the face area. And then OpenFOAM uses phi HbyA. And you can see the equation is really similar, except instead of using the velocity vector, we're using HbyA. And this notation of phi HbyA is there to remind us that this is the volume flow rate, or the volume of fluid that's pushed across a face each second by HbyA rather than the velocity field. So hopefully that small difference, hopefully you've been able to understand that now. And if we return back to the pressure equation and we look at the right hand side, you can really see what this actually means. We've got the sum over the faces of this quantity phi HbyA that we've just calculated. So what this really means is that the source term in the pressure equation for incompressible flow is the sum of the volume fluxes, so the volume of fluid that's pushed across each of the faces of the cell by HbyA. We sum them together, and that sum will not be equal to 0. This is a source term, and that sum is the source term in the pressure equation. And another way you can think of this in an inverse way is that in an incompressible flow field where the density is constant, if we worked out the volume of fluid that was being pushed across each face by the velocity field, if we summed all of those together, then the sum would be equal to 0. The sum of the volume flow rates across each of the faces of the cell would be equal to 0. The net volume of fluid that's being pushed into the cell is equal to the net volume of fluid that's being pushed out of the cell. And that's what the continuity equation physically represents. But remember that we split that velocity vector u into HbyA and a pressure gradient term. So what we're doing here with the pressure equation is we've kind of split out that continuity equation. If we can find a pressure field that satisfies this equation, then the sum of the volume fluxes from HbyA, which are not equal to 0, will balance the left-hand side from the pressure gradient. And if these two terms balance, if we think back to our original equation for u is equal to HbyA minus 1 over A11 times the gradient of the pressure field, then those two terms will be equal and the continuity equation will be satisfied. That may be quite confusing for you, so usually it's just best to think of this pressure equation directly, and that the right-hand side is just the sum of the volume flow rates across each of the faces from HbyA rather than the velocity field. And this is exactly why we need to calculate HbyA. We calculate HbyA and we calculate the volume flux across each of the faces from it, and then that's the source term for our pressure field. So that was probably a lot for you to take in, but I'm really hoping that you've developed some good understanding now of what the incompressible pressure equation is like and why HbyA is important. But just to wrap up, you'll remember that HbyA is calculated at the centroids of all of the cells in the mesh after the momentum equations are solved. We then use interpolation to get the value of HbyA at the face centers, and then we evaluate the flux, or the volumetric flux, from HbyA across each of those faces. We sum them together for each cell, and that becomes the source term in each cell in the mesh. And You'll remember that HbyA is an artificial quantity. It doesn't really have a real meaning. It's not a real field. But the reason we introduce it is so that we can calculate and evaluate this source term for the pressure equation. It's an intermediate field that we have to calculate if we want to assemble and solve the pressure equation in this form. So that brings me to the end of the video. I'm really hoping now that going through these two detailed lectures, you've now got a good understanding of what the field HbyA actually means, why it's calculated, and actually what it does in the algorithm adopted by OpenFOAM. If you found the video useful, let me know in the comment section. I really enjoy hearing from you, and if you have any other suggestions for any parts of OpenFOAM or any other algorithms which you'd like to go through in a bit more detail, let me know and I'll consider them for my future videos. Once again, thank you all very much for watching, and I'll see you in the next video.